Good day. For those of you who don't know us, we're the instructional staff for ECU 150, Professors Hiren Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to carry on our conversation on arrays. However, now we're going to get a little bit under the hood. We're going to look at how arrays are implemented specifically in C++. So in this topic, we're going to see how arrays are passed to functions, and this behavior is going to be unexpected given what we've seen up to this point. We will learn that arrays identifiers themselves have a value, and we will see how that value works. We will see how that corresponds with the passing of arrays to functions, and see that local arrays are treated as const, but parameter arrays are not. In the previous topic, we saw how to create arrays and how to use them. You can now use arrays to solve problems, and if you know how to use arrays in C++, you can use them in other languages. We saw that an array stores a fixed number of entries, and that number of entries is known as the capacity of the array. We also saw that entries of that array can be accessed with either a literal integer or an instance or local variable of an integer data type, and that is known as the index into the array. The index must be an integer value between 0 and the capacity minus 1. Having the index go between 1 and the capacity is the single largest mistake most first-year students make. Now, what's nice about this is all you really need to know to use arrays to solve problems. However, now we're going to look at the implementation of arrays in C++ and see how they make sense. We're going to see how to pass arrays to functions. We're going to see how that is implemented. And also, this is going to lead us to understanding addresses and main memory. So that will be the next topic. Now, the first difference between arrays and local variables, where the local variables are declared to be of primitive data types, is that local arrays cannot be assigned to. Here's a program, and in this program, I've declared two arrays, and I've ensured that they're both the same capacity. I then assign the first array the value of the second array. If you try compiling this, we get an invalid array assignment. So C++ is not allowing you to assign one array to another. It's almost as if array identifiers, when they are local variables, it's almost as if they are declared const. However, if an array is actually explicitly declared to be const, it is the entries of the array that cannot be changed after the initialization. So for example, here I have an array of prime numbers, or so it seems. I've also declared this array to be const. However, if you'll notice, the last entry is 25, and that is not the 10th prime number. The 10th prime number is 29. So I could try to fix that by assigning to the 9th entry of the array. However, in trying to compile this, we note that it states that there's an illegal assignment of a read-only location. Specifically, I was attempting to assign to primes 9. This is essentially a design feature in C++ and C that local arrays are not assignable. Basically, the assumption is that local arrays are temporary and they are to be used to solve problems, and when the function returns, they are no longer necessary. If you actually wanted to, say, copy all the entries from one array to another, you must do so explicitly using a for loop. So assuming that both of these two arrays, first array and second array, have the same capacity, then this little routine will copy all the entries from the second array to the corresponding locations in the first array. Now in C++, there is no mechanism whatsoever to ever be able to return an array from a function. So this is the correct notation that you would use if you wanted to indicate that f was returning an array. However, if you were to try to compile this, it would essentially state that this is not allowed. Again, local arrays in C++ are meant to temporarily store information for the duration of the function to solve a very specific problem. C++ does not want to get into the behavior of trying to copy over entries of one array into another, which could potentially be rather expensive. C++ is never going to create a new array for you and copy the entries from one array over to another for you. That is something you must do explicitly. Also, we cannot return a local array, as the scope of the local array was the function itself. So if a local array is declared in a function, you can't return that array. Now, fortunately, we're going to see that there is a solution for this, and we will see how we can create, manipulate, and return persistent arrays, but it will not be done with the notation we have used here for local arrays. For that, you must understand addresses, and later on we're going to be looking at pointers. Now, local arrays can be passed as arguments to a function, and you may initially suspect that the notation for the function declaration is as follows. Average here takes as a single argument an array of capacity 10, and of course it returns a double. The issue here is that, well, what happens if you want to take an average of 11 entries or 7 entries or whatever number of entries? It seems rather artificial to have to write a different average function for every single different capacity of array. And so this is really suboptimal. Not only that, C++ does not actually check to ensure that any argument is of the specified capacity, which is also a little bit peculiar, but part of the programming language. The solution is therefore to instead have the capacity passed as a separate argument. So the first parameter of this function is called array, and it is an array of doubles, but the capacity is not specified. Instead, the capacity will be passed as a second argument. So that gives us the number of entries in the array. Let's now implement and use this function. So here we have a function double. We have a local variable sum, which is initialized to 0. We add to that local variable the value of each of the entries of the array. We then return the sum divided by the capacity, and that will calculate the average of those entries. So at the bottom here we have an array with capacity 5, and it's initialized with the values given there. We then print whatever is returned by calling average with the name of the array, data, and the capacity we expect, 5. And so the output would be, in this case, 104.02. If we pass that same array over, but the second argument was 4, then it would just simply calculate the average of the first 4 entries of the array. If we pass the second argument 6, what would happen? Well, in that case, the function average would try to access index 5, which goes beyond the end of the array. But C doesn't matter, it will just read whatever value is stored there. And so if you call average with the first argument data, but the second argument 6, then it will calculate the sum of the 5 entries we see there, plus whatever value is stored immediately thereafter. And then it will divide that total result by 6 and print it out, which may seem a little bit odd. And yes, that would be a programmer error. That would be a bug, but it may be difficult to find that bug, especially if the capacity of the array was not as obvious. Now, one solution to having the capacity of the array being 5 is to actually have a separate local variable declared const that stores that capacity. So in this case, here we have the local variable data capacity, and then we don't have to worry about what value that stores. We will simply pass that to the average function. Now here's a slightly different function. This function is going to print the entries of an array. Hence, it returns void. There's nothing to return because all of the output will be sent to the console. We have the same first 2 arguments, and if the capacity is 0, then we will simply return. So it is possible in C++ for an array to have capacity 0. If, however, the capacity is 1 or greater, the first thing we will do is print out the first entry. Following this, we will have a for loop that goes not from 0 to capacity minus 1, but 1 to capacity minus 1, because we've already printed the first entry. And for all subsequent entries, we will print a comma and then the value stored at that particular index. Having finished, we will simply print an end-of-line character. Here's another function. This takes an array, but instead of printing it to the screen, is going to convert the entries of the array into a string. So again, we start. If the capacity is 0, we'll just return an empty string. Otherwise, we will have a local variable of type standard string, and we're going to call this the return string, and it will be initialized with the first entry of the array converted to a string. We then run a for loop, again, from 1 to capacity minus 1, and with each iteration of the loop, we will concatenate on to the end of the return string the concatenation of a comma and the next entry of the string. All right, straightforward enough. We will then return the return string to the user. So here we are using both of these functions. First, we will print the array to the screen, which does all the printing for us, and then we will print the string that the array is converted to the console. If we execute this code, we do notice that the output is slightly different. So as you can see, when a double is printed to the screen, the output is slightly different than when a double is converted into a string. But it still works. Now here's a different function. Here the array is being passed to the reset function, and inside the array, each of the entries of that array are being set to 0. Now, as you may recall previously, arguments were passed to functions by value. So a change to a parameter did not make a change to the original argument unless the argument was passed by reference, in which case the arguments were restricted to things that could be assigned to, say, local variables. Here we are going to call reset on data. So one would expect that the output is just the same entries of the array prior to calling the function. However, if we compile and execute this program, the output is 5 zeros. So it seems as if the reset function has actually changed the original array. Now wait a second. Aren't parameters passed by value? That is, wouldn't you expect that a copy of the array is sent to the function, which is then manipulated and then discarded once the function exits? Well, this is going to sort of be a problem, especially once you start having very large arrays. Suppose you passed a function with 1,000 entries in it. So the capacity is 1,000. This would mean that at runtime, to call or to pass an array to a function would require 1,000 copies. That's going to get very expensive. And whereas there may be applications for this, this probably isn't in the best interest of the programmer. Also, let's make an observation. Remember when we passed by reference using the ampersand? We could not pass an arithmetic or logical expression. We could only pass something that could be assigned to. Well, in the same way, if we are passing an array to a function, we can't pass data plus 1 or something else. We can only pass an array. So if you can only pass the identifier of the array, then I guess it would be okay if the behavior was different from when you were passing, say, an algebraic or arithmetic or logical expression. So the question is, what is actually being passed to a function? Well, here we have a program that prints not the entries of the array, but rather it prints the array itself. Now you may be wondering, well, what does that do? What happens if you print just the array identifier to the console? Well, we're going to try it out and see what happens. After we print the identifier of the local array data, we will pass that local array to some function, and some function is going to print to the screen the parameter value. All right, let's execute this and see what happens. We get 2 hexadecimal numbers, and those 2 hexadecimal numbers are equal. So it seems that both data and the value of the parameter array are the same. So it's almost as if that value, FFFFCB80, is the value that is being passed to the array. Now, you may recall that this is a hexadecimal number. So we have 2 hexadecimal numbers, and the values of the 2 arrays are equal, whatever this represents. Now, if you were to take this same code and compile it on your computer, you may not get exactly these numbers, but whatever numbers you do get, both of your outputs will be the same. So, to try to understand what this means, recall that an array of capacity n stores entries of a given type, and each entry in that array occupies a fixed number of bytes. So, for example, an int occupies 4 bytes, and so an int array of capacity 10 would store or require 10 times 4 bytes or 40 bytes. A double occupies 8 bytes, and if I had an array of 7 doubles, then that would require 56 bytes. A bool requires only 1 byte, so therefore an array of 100 bools would require 100 bytes. So basically, this array needs to be stored somewhere in main memory, and the value of the array is the address of the first byte that the array occupies. So basically, the value of the array is an address in main memory, and it is at that location in main memory that those entries of the array will be stored. Now, let's consider the following program. In this program, all we have are 3 local arrays. All of them are storing int, and therefore each int occupies 4 bytes. The first array has a capacity of 12. 12 times 4 is 48, therefore it occupies 48 bytes, or requires 48 bytes to store those 12 ints. And in hex, 48 is 30. 3 times 16 is 48. Next, we have an array of capacity 20. 20 times 4 is 80. And 80 in hex is 50, as 5 times 16 is 80. The last array has a capacity of 52. This requires 208 bytes, because 52 times 4 is 208. And in hex, this is C0. So 208 in hex is C0. And this is because 13 times 16 is 208. Now, all we're going to do is print those 3 addresses. All right, so we compile this program, execute it. You may get something slightly different, but it's going to be similar. You're going to see 3 addresses printed to the screen. Now, which is the smallest of these hexadecimal numbers? Well, if I gave you these 3 decimal numbers, it's very quick. You'd notice that the first 5 digits are all the same, and all you'd have to do is look at the 6th digit to see that the third has a 1, whereas the first 2 have a 2, and therefore the third number must be the smallest of these 3 numbers. Okay, going back to these, we notice that the last number is FFFFCA, whereas the first 2 start with FFFFCB. Therefore, the third number is indeed the smallest of these 3 hexadecimal numbers. Also, if we take that last address and add to it the value D0, well, D is equal to 13. B plus 13 is C, D, E, F, 0, 1, 2, 3, 4, 5, 6, 7, 8. So it was an 8, but we cycled through 0, so there's a carry. So we carry a 1 over. 1 plus A is B. And so, yeah, we notice that this is the second address. All right. Now let's take that second address and add to it 50. Well, 5 after 8 is 9A, B, C, D. And we'll notice that, again, there's no carry, so the answer is just D0 in the last two digits, and that was that the first address. Graphically speaking, this was the output we saw. Well, if this is the first address, then 208 addresses after that is that address, and those 208 bytes are used to store that third array. Following this, there are 80 bytes. Those 80 bytes are required to store the 20 entries of the second array, and that third address, that's 80 addresses after that other address, the previous address, and the next 48 bytes are used to store the first array. All right, now one thing that's important to remember is the address that is passed to a function when you call a function with an array as an argument. That address is actually passed by value. So the parameter only takes on the value of that address. So we do not pass by reference. It's more that that address is passed by value, but when you now change something in that array at that address, you are also changing the array of the original argument. Let's go through this and see what happens. Okay, so let's look at this output. Here inside main, I have an array of capacity 4, and I'm going to print out the address of that array. All right, so data is located at this position in memory. We will now call f and see what happens. Now, the first thing inside f, we notice that there is a local array of capacity 5, and I've made the entries significantly different so that we can see this. All right, next, param. What's its value? Well, param has the same value as data, as that address was assigned to param when the function was called. Consequently, right now, param points or stores the same address as data, and therefore any index into param is an index into the array data. Local, on the other hand, is at a different location. It's close to, but it's at a different location from the array data. If I print the entry of param 3, I get the fourth entry of the array data. Recall that the fourth entry of an array is technically at index 3. If I was to assign to param 3, then data 3 would also be changed because we are changing a value at the same location. Now, at this point, we're going to assign param the value or the address of local. All right, and I'm just going to indicate that in the output to show that we've done that. Now, when I print the value of param, I get the address of local. And local has remained unchanged since all we did was assign it to param. However, now, when I ask for index 3 of param, I'm going to get index 3 of the local array, and the fourth entry of local is 1000. Okay, so now we return from the function, and let's just print out the value of data again, and we notice that data is unchanged. It has the same value that data had prior to calling the function f. So this just emphasizes that if you pass an array as an argument to a function, the address of that array is passed by value. Okay. So, following this lesson, you now understand that arrays do store an address in memory, and it is at that address in memory where that array is stored, and the compiler will make sure there's enough memory there for that array. You understand that arrays, when they are passed to functions, are passed by this address value, and they are passed by value, so you cannot change the value of an array. You cannot even pass an array by reference in C++ ever. So therefore, a change to an entry in a parameter array changes the corresponding entry in the argument array. And while local array identifiers cannot be assigned to, parameter array identifiers can be. Okay, here are the references, the colophon, and a disclaimer. Cheers!